right, let's get started. We're going to continue talking today about cross-validation. And so remember the context here is we are doing predictive modeling. And specifically, we have in mind a response variable that may be numeric or categorical. And we want to relate it via some arbitrary function f to some predictor variables, inputs. One simple version of this could be a linear regression model. Y is equal to intercept plus slope times x plus random error. But the Introduction to Statistical Learning book has lots of different types of f functions. Regression, logistic regression, linear discriminant analysis, random forests, all those things are different choices of f. The way that we proceed with building a predictive model, suppose we want to, we work for Capital One and we want to predict, given the characteristics of a customer and a particular transaction, I want to predict whether this transaction was a fraudulent transaction. In order to build a model to predict something, we need to have data for which we know that's something. So the way we begin is by getting training data. Here's n individuals for whom we have the predictor variables, the p predictor variables in x, and we have the response, the quantity that we would like to predict. These are training data. So given training data, we can, if we specify the type of function f that we're going to consider, like regression model, we can estimate that model. We can use the training data to fit a particular model. So that would look like, so let's say, given a particular form for f, we would use the training data to estimate f. So that would give us an f hat. Might be an estimated regression model, beta 0 hat plus beta 1 hat times predictor variable. We can then make predictions. A prediction would be y hat. That is our estimated prediction function evaluated at a particular set of covariates. So for a middle-aged female with an average balance of $2,000 a month who has never missed a payment on their credit cards, what's the estimated probability that this particular $5,000 transaction at Best Buy was a fraudulent one? Somebody stole her credit card. We can make a prediction. Given that there's lots of different choices for f, many different models, and for each model there's many different flavors of that model. For just about any predictive model, there's always at least one parameter that we can tune to try to get it, tweak it to make it be as accurate as possible on our training data. So a key part of this predictive modeling process is to assess the accuracy of a given model. If I have 10 models that I'm going to consider, I would like to use the model at the end of the day for predicting credit card transaction fraudulence to be the one that's most accurate. So we're currently thinking about how do we estimate accuracy. We're interested in, let's say, prediction accuracy. What we mean specifically by prediction accuracy depends on the context. For example, last time we considered what if the response is binary? Like in the baseball data, you're either in the Hall of Fame or you're not. If Y is binary, then we have this 2x2 breakdown of possibilities. Each player is either in the Hall of Fame or not, and we're going to make a prediction for each player that they're either in the Hall of Fame or not. So here are cases where we made the correct prediction, and here are places where we made mistakes. We talked last time about because there are two types of mistakes, you can either incorrectly predict that a true Hall of Fame player is not in the Hall of Fame, or you can incorrectly predict that a true non-Hall of Fame player is in the Hall of Fame. Each of those are different types of errors. And sometimes in practice, one or the other one is more important to you. Suppose we were predicting whether somebody has cancer or not. You go to your medical doctor clinic, they take a blood sample, they do some assay, and they get back a prediction. Probability you have prostate cancer is such and such. Based on that probability, you make a decision. I claim you have cancer. I claim you don't have cancer. So which case would you, if somebody's going to make a mistake in predicting for you, would you rather be incorrectly told you don't have cancer, or would you rather be incorrectly told you do have cancer? So if you do have cancer and somebody tells you you don't, then you're not going to get treatment that you need. That could be bad. If you don't have cancer and somebody tells you you do, you may be submitted to treatment that you don't need. And some of the treatment for cancer is very invasive. But you can at least consider the possibility that we would be worse, we would be less happy with a mistake of one type than another. I'd rather take some medication that may not make me feel good but won't kill me, even though I don't have to, than not get treatment that could prolong my life. So I just mean to say, first of all, there's multiple ways that you can make mistakes when you're making predictions, in particular when Y is categorical. And number two, you should consider all possible ways and consider whether they are all interchangeable to you. Is one type of mistake just as relevant to you as another type of mistake? Or, like you're doing in the baseball data, should you differently weight the two different types of errors? So if Y is binary, we have this breakdown. Y could more generally be categorical with more than two classes, in which case we would have a bigger than 2x2 table of mistakes. By the way, this table, so let me say in the more general categorical case, if Y has K categories, then there would be a K by K matrix. So class 1, class 2, ... class K. with truth across columns and claims across rows. That's just an extension or a generalization of the 2x2 table in the binary case. Both of these things, these tables of cross-tabulations, are called confusion matrices. So basically, when you build a predictive model, if you cross-tabulate your predictions with truth, that's called a confusion matrix. And it's a kind of concise way of representing how accurate you are. Notice in addition to spelling out how each error happened exactly, like which cell in the confusion matrix an error belonged to, you could alternatively characterize accuracy overall with an overall misclassification rate. This is just the proportion of predictions that are wrong. If we have n training individuals, we could make a prediction for every single one of them and compute the proportion of those predictions that are not right. That's a single number summary of performance or accuracy. That is potentially problematic, using that as your overall accuracy, because consider the baseball data, for example. In the baseball data, we have 1,000 players, and less than 10% of them are in the Hall of Fame. It's like 8%, I think, who are in the Hall of Fame. So suppose we, as our predictive model, suppose we said, I predict no for every single player. It does not matter what your statistics are, I will predict no for every player. The accuracy, the overall accuracy, or the flip side, the overall misclassification rate, would be really small. If I say no for every single player, then I will be right for 90% of the players. If only 10% are in the Hall of Fame, then saying no all the time results in a pretty respectable accuracy of 90%. But in reality, that's a worthless prediction algorithm. So just looking at the overall proportion of errors made is not typically sufficient. That's why we like to look at confusion matrices, because you can have a rosy misclassification rate when it's really a terrible predictor. Another relevant quantity that is used is balanced accuracy. You're asked to use this in your homework. Balanced accuracy is, at least in a binary case, it's some constant times sensitivity plus 1 minus that constant times specificity. Or I guess we could say, let's say W and another constant, call it just V, divided by the sum of those constants. A weighted average of sensitivity and specificity. Simplest case would just be the straight average, sensitivity plus specificity divided by 2, with W and V equal to 1. In your homework, you're going to use sensitivity plus 3 times specificity divided by 4. That's intended to kind of upweight, incorporate more heavily specificity. That is incorrectly classifying non-Hall of Fame players as being in the Hall of Fame. Because there's so few players in the Hall of Fame, you can have a high accuracy by just predicting no all the time. So in order to force our model to do decently on those players who are not in the Hall of Fame, we upweight the specificity. So all of this is in the context of assessing the accuracy of a predictive model. When Y is categorical, we think in terms of confusion matrices. If Y is numeric, we don't have accuracy rate. We don't have a misclassification because we're predicting a numeric variable. So every prediction is going to be off, almost surely. We're not going to be able to predict a continuous number perfectly. So misclassification rate is not the most appropriate error measure when Y is numeric. Instead, what we often use is something like a mean squared error. So this would be, for example, the average squared difference between truth and prediction. I don't expect Y hat to equal Y generally, because Y is numeric, potentially continuous. So an alternative way to gauge how wrong we are is how far away do we tend to be from the truth? What's the average distance between our prediction and the truth? That's a mean squared error kind of quantity. Regardless of whether Y is categorical or numeric, there is some quantity that makes sense for us to compute to assess and quantify accuracy. So the point that we talked about last time is that we have to be careful how we compute that accuracy. Let's think mean squared error for a second. Or let me state this. How to estimate error rates or accuracies. So whether it's misclassification rate or balanced accuracy or mean squared error, how should we estimate these quantities? One possibility would be use the training data to fit F, then compare truth to prediction on the same training data. In the baseball data, we have 1,000 players. We could take those 1,000 players and fit, say, a linear discriminant analysis model, and then turn around and make predictions using that model on the same 1,000 players. So I'd have truth, and I'd have prediction for each player. I could compute an accuracy, an error rate, balanced accuracy, a misclassification rate, any of those, I could compute that with those quantities. What we saw in the last couple of lectures, though, is that that's not what we want. Because if you build a predictive model and then assess its accuracy using the same data, the danger is that you overfit the training data. If your goal is just to predict accurately with a given data set, you can make it as complex as necessary, or you can make it more and more complex, and you will get more and more accurate at predicting. With the extreme being that eventually, if you make your model sufficiently complicated, you'll interpolate your training data. You will perfectly predict with your training data. But that's deceptive because that's specific to that training data set. And if you were to try to apply your method to the more general population, like if we're predicting cancer, and I have a training data set of 10,000 people, I might be really accurate on those 10,000 people, but what I really want to speak to is how accurate will I be in the general clinic setting when new people walk in the door and we make predictions for them. So this is one possibility, but it's a bad choice. So we don't do this. If we don't do this, there are two alternatives that we'll learn about. One is, so let's say alternatives. One is to split the training data into train and test sets. In the baseball data with 1,000 players, we could take 667 of them, randomly selected, to be our training data. We're going to build our model, we're going to tune it, compare between different choices of models using those players. The remaining 333 are going to be held out and not looked at all until we have decided which model we want to use. Based on the training data, we consider a bunch of models and we find, well, this one right here seems to be most accurate. My formal assessment of how accurate it is would be based on applying it to the held out test individuals. I would build a model with the 667 randomly selected players. I would claim its accuracy based on the accuracy I get when I make predictions on the remaining 333. For reference, let me show you the part of the Introduction to Statistical Learning that is relevant. Let's see if I can find it. There's a part of the book that has some more detailed discussion of this. I'll have to find it. I didn't see it immediately. But I'm still trying to motivate where we are currently in the nodes. We're building a predictive model. A big part of doing that is assessing how accurate it is. Accuracy means different things depending on the nature of the response variable. Regardless of the nature of the response variable, though, to estimate an error rate in such a way that is generalizable to the population, we need to use care. One bona fide way to do that is to do the train-test split. If you have a large sample in particular, lots of data, like I'm working right now with some people in the provost's office, and we have data on A&M students, 40,000 of them over the past 3 or 4 years. We have data on like SAT scores, ACT scores, ethnicity, gender, first generation in college, and all of that. And we're trying to predict, yes or no, will each person graduate from the College of Science? So it's a prediction problem. And we have 40,000 people, lots of people. So we took 2/3 of them, set them aside. That's our training data. And 1/3 that was randomly selected, we're holding out as a test set. And we're building predictive models like we're learning about right here, logistic regression, LDA. So this type of stuff is very common nowadays. Predictive modeling, we're going to build a bunch of methods, need to assess their accuracy. You either do it with splitting the data like this, or you use a trick, a computational trick called cross-validation. And cross-validation is basically a computational trick to mimic the train-test split. If you have an abundance of data, there's no reason not to train-test split. In fact, that's optimal. If we were to find the relevant part of the Introduction to Statistical Learning book, they state that the optimal way to assess the accuracy is a train-test split. Cross-validation is an alternative that seems magical in that it allows you to estimate the generalizable accuracy without train-test split, but it does come, that magic comes with a penalty, and if you could, you would avoid it. But people use cross-validation a lot in practice, especially when they have relatively small sample sizes. I only have 100 individuals. Each one of them cost $1,000. I don't want to set aside 33 of them just for assessing accuracy. That's a hard sell to somebody who has collected their own data. Cross-validation is an alternative that allows you to use all the training data with a twist and gives you at the end of it an accuracy estimate that is as if you train test split. So our current chapter is all about cross-validation. It also has Bootstrap in it. I'm not going to emphasize Bootstrap in the context of predictive modeling. Bootstrap and cross-validation share some similarities. Both of them are kind of resampling techniques. But cross-validation, we'll see, is for estimating accuracies or error rates, whereas Bootstrap is generally used for other purposes. In particular, what Bootstrap can be handy for with predictive modeling, remember Bootstrap is, all it is a resampling technique for estimating a sampling distribution. If you were to repeat a study and compute a particular statistic each time, what would that statistic look like across the replications? That's a sampling distribution. In the context of predictive modeling, a relevant statistic is accuracy. Sensitivity, specificity, misclassification rate, mean squared error, all of those are statistics. So in addition to reporting an estimated accuracy, like here's a predictive method for cancer, and the misclassification rate was estimated to be 90, or let's say 10%. Is that 10% plus or minus 2%, or 10% plus or minus 0.5%? Bootstrap would give you that information because it tells you about what that estimate will look like across replicates. It gives you a sampling distribution, and part of a sampling distribution is the variability. So Bootstrap is useful in predictive modeling, but what it's usually used for is getting a standard deviation for your accuracy measures. My predictive model is 90% accurate, plus or minus 1 percentage point. That plus or minus you can get with the Bootstrap. But the resampling trick for getting a generalizable estimate of accuracy is where cross-validation comes in. All right. So just reiterating things we've already said, we have a distinction between types of error rates when doing predictive modeling. We can talk about training error and testing error. Training error is the error that would happen if you applied your predictive model to the same data you used to build the predictive model. Test error is what happens if you apply it to a held-out test set. And we have this type of relationship where a horizontal axis is model complexity, vertical axis is error, blue is training sample, red is test sample. As you increase the complexity of your model, you necessarily decrease the error in the training data. That's a problem because eventually you end up overfitting the training data. What we really care about is the red curve. That's the generalizable error. This is the error you can expect to apply when you go out into the general population. You go make predictions for new people in the clinic. And this is a common pattern where increasing complexity helps up to a point, beyond which it hurts. Think of it like you're fitting a regression model, and you have a whole bunch of predictor variables that could be in the regression model. Some of the predictor variables will be informative and belong in your model because they help substantially decrease the error. Other predictor variables may not contribute much, if anything. And so if you have a predictor variable that you're considering putting in or not putting into a regression model, if its coefficient is really equal to 0, if it really has nothing to do with the response, then adding it to the model will increase error because you're adding a noisy component to your model. That's why beyond a certain point of model complexity, you see the red curve going up. Oh, that's what I was looking for. Okay. One more thing I wanted to mention on this picture. Up at the top, they have, top left, high bias, low variance, pointing towards the left. And over at the right top, they have low bias, high variance, pointing to the right. Let me comment on that here. This discussion, this language, shows up, I think, in the statistical learning chapter. But without going there, let me just say something brief. The general idea is that less complicated, simpler models will tend to be more biased in their ability to represent a real-world relationship. Like a simple linear regression model, I'm going to say that height is linearly associated with weight. That's generally true, but it's not perfectly linear. It's not a perfect deterministic relationship. So fitting a line might give us the gist, but it's going to be biased because it's not a perfect model. A simple model, though, like a linear regression model, while it may be biased, it may also have low variance. So there's this dual importance when you're estimating things in statistics of bias and variance. If you're going to estimate a quantity, then you want, ideally, on average, to estimate the right value. If we're trying to estimate the average income in a particular population, an unbiased estimate would be one that if we got a sample and estimated an average, and then did it again, and did it again and again, and we had all these averages, that on average, the average is equal to truth. Is an unbiased way of estimating something. Separate from bias, though, there's also variability. That repeating the computation of your statistic. You go get a sample and you compute a statistic. Then imagine repeating that. You do another sample, you recompute your statistic. Envision the sampling distribution of that statistic. If it's centered at the truth, then your estimate is unbiased. On average, your estimate will equal the truth. Also, think about how spread out the distribution is. From sample to sample, how variable is your statistic? The bias and the variance are two core ways of characterizing an estimate. In fact, there is a interesting relationship that says for a numeric estimator, so let's say that theta is a numeric parameter, and theta hat is some estimator. Like, go get a sample from this population, and my estimator theta hat is add up all the values and divide by n. It's the sample average. That's one estimator. Another estimator might be a median or an interquartile range. But for an arbitrary estimator, a common way to characterize its accuracy overall is mean squared error. And as we've said, this is an average squared deviation. This is here written in terms of an expected value, so that's a theoretical average. And it turns out that the mean squared error of this equals the bias of our estimator squared plus the variance of our estimator. That's in the Introduction to Statistical Learning book. But you can show that the mean squared error of a numeric estimator is equal to its bias squared plus its variance. And so there is what's called a bias-variance trade-off. You might have an unbiased or very nearly unbiased estimator, but if it has a high variance, it may still be suboptimal. Overall goodness of an estimator you can characterize with mean squared error. You can have low bias but still have high variance. You can have low variance but high bias. The best estimators will be ones that balance this well and are kind of low across both measures, bias and variance. That's what this is referring to here in the picture. Typically, simpler models, less complex models, will come with higher bias because they're not complicated enough, they're not complex enough to really accurately represent a real-world relationship. So they're like a rough picture bias. But what they have going for them is low variation, low variability. The idea behind low variability for simpler models is, suppose we have a picture like this, a numeric predictor variable and a numeric response. And suppose we collect some data. And that's our scatter plot. We're going to consider two possible models for relating y to x. One is a linear model, and the other is, let's say, a natural cubic spline. So it's a curve, a curvy model. Both of those curves were fit to these training data. But now imagine that we go to the same population and we take a new sample. If this is 50 individuals on the scatter plot, we go get a new 50 individuals and we make a scatter plot of them. And we fit these two models to them. Which of these two models do you think is going to change more? If you were to repeat this study, I sampled 50 individuals from the population of interest, and I fit a line, and I fit this cubic thing. Now I go get a new 50, and I make its scatter plot. Which of the two curves would you expect to look different, most different in the new data? The curvy one. The line is so simple, it won't be so affected by the dots moving around. Whereas the curve, if you move the points around, the curve is going to be more affected by where the points go. So the idea here is simpler models will tend to be less biased, more biased, but lower variance. From sample to sample, that line doesn't change as much as the curvy cubic thing does. Simpler models, high bias, low variance. More complex models tend to have lower bias because they're more complex and therefore able to really capture real-world complex relationships. But the penalty for that is that they have high variance. So in terms of building a predictive model, we care about both bias and variance. And our goal then is to find a happy medium between complexity and accuracy. All right. So I went through these next couple of slides last time, I think. Best solution, as I said earlier, for estimating accuracy is the designated test set. If you have a big enough sample size and data are in abundance, go ahead and take a third of your data and set it aside just for testing. That has the least amount of assumptions or ways it can go wrong with estimating accuracy. Other alternatives, I mentioned there are some mathematical adjustments to training error rate, such as AIC, BIC. Or can do cross-validation. Let's go here, slide 9, and we'll finish on this slide. The general algorithm for cross-validation. It's referred to generally as k-fold cross-validation, where k is something you pick. K might be 1 or 5 or 10. Those are all common choices. There's no perfect choice for k, but I think the consensus among experts is that 5-fold or 10-fold cross-validation is the best bet as a generic tool. Here's the idea. We randomly divide our training data into k equal-sized parts. Suppose we're doing 5-fold cross-validation. K is equal to 5. In the baseball data, we're going to divvy up our 1,000 players randomly into 5 equal chunks. And then we're going to do a for loop. In the first iteration, we'll take the first fifth. I took my 1,000 players and I randomly allocated them into 5 equal groups. Cross-validation is loop 5 times. In the first iteration, the first fifth is your test data, and all the remaining 4/5 is your training data. So use the 4/5 to fit your model, and then assess it on the held out 1/5, and store the accuracy. In CV fold 1, the accuracy was 82%. Then you iterate and redo the whole procedure. Now the second fifth is your test data, and the remaining 4/5 is your training data. So again, you build the model from scratch with the training data, and you assess it on the test data. In that iteration, maybe your accuracy was 87%. Write that down. Iterate again. At the end of this, you will have 5 accuracies, 1 for each CV fold. And the overall cross-validation based estimate of accuracy for the model you fit is then the average of the 5 accuracies. And that quantity is comparable to a bona fide test set that is the ideal. It's not perfect, and it has much higher variance than the test set approach. But at least in expected value, it's a valid way to estimate the generalizable accuracy. So here's an illustration visually. Break the data into 5 sets if we're doing 5-fold cross-validation. Right. Okay, so we'll pick up here on Friday. I think you should have I guess in order to do the homework, you need some examples of LDA and QDA. So I will post some instructions on discussion board today for some places you can look to get up to speed. But you now know how to do cross-validation. In the homework, I asked you to do leave one out cross-validation. If k equal 5 is 5-fold, then k equal 1 is leave one out. So instead of taking a fifth as your test data, you take just one individual, and you iterate n times. So watch for a post from me on tips with LDA and QDA. Okay, and I'll see you Friday. Thanks.